Now we are into temperature stresses. They are also called as thermal stresses. We know when temperature increase or decrease, what happens to the material? The material will either expand or it will contract. In either case, if you do not provide enough provision for the expansion or shrinking of the material, you can have some cracks developed in the material or stresses will be developed into the material. These stresses are called as what? These stresses are called as temperature stresses, or even otherwise we can also call it as thermal stresses. Here you can see in the picture, what has happened now. In this picture, we see that there is some amount of gap provided here. See, there is a gap here, is it not? If this gap is not there, if you have a solid straight rail, then see here what will happen because of the temperature. See here, buckling has happened, is it not? So this is the problem. So what we need to do, we need to provide some amount of gaps for this expansion or contraction. We also know that each and every material has a different property. Okay, so some materials expand very fast, like for example you have mercury. It is a liquid metal which is used in thermometer. With the change in temperature, the expansion of the mercury is very much, it expands very fast. We have iron, it expands in a different way. We have copper, it expands in a different way. So there is something called as coefficient of linear expansion. Okay, now see here, we have a material right in front of us. This material initial length is how much? Initial length is L naught. So now when we increase the temperature, what happened? There is some amount of expansion here, that is delta L. Okay, delta L is the free extension due to temperature rise. This alpha is coefficient of thermal expansion. This is the property of the material. Delta T is the temperature change. Initial temperature is T1, final temperature is T2, means I can say delta T is equal to T2 minus T1. This is your delta T. Okay. Now, there are three possibilities to happen. So now when the material is allowed to expand ala tool without any obstruction, what is happening? The material has elongated here. Okay, there is no stress induced. So there is no stress induced. You have just delta L, this expansion. You can easily find out alpha into delta T multiplied by L naught. Okay, this is one case. Case number two. In case number two, what I am doing is, see, in case number two, the material, I did not allow it to expand. So you can say that this wall was here. Which one? This wall was here. I am pushing it back. So when I push it back, what will happen here? I will have compressive stresses induced in the material, is it not? There is some amount of stress induced in the material. The formula is there. Delta L is what? Delta L is alpha into T into L naught, is it not? So now we also know that the stress is what? Stress is nothing but when I can write E is equal to stress by strain, right? So I can write it as what? E is equal to sigma by E, right? Sigma is what? Sigma can be written as, uh, see, this is delta L by L, I can write, is it not? Delta L by L, and also you can write it as what? Just 1 minute. Let me just do it this way. Now see, P can be written as what? Sigma is nothing but P divided by A, is it not? E is what? Delta L over L. What happened to this? This went up, is it not? Is equal to E. So what can I write now? I can also write delta L is equal to P L by A E. F L by A E or P L by A E you can write. Okay. So this you have got. This is the formula for delta L. So now what can I do? I can put this for delta L. This delta L can be replaced here by this value. See here is equal to alpha delta T into L naught. Okay. So now if I am pushing it back, that is I am pushing back this much of delta L. If I am pushing back this much of delta L, that is this one can be replaced by what? PL by AE. P by A is sigma. So what can I write? Sigma into L by E is equal to alpha into delta T into L. Is it not? This L and L gets cancelled. So I can write alpha sigma is equal to alpha into delta T multiplied by E. This is the formula. That's what you see over here. Okay. So if you push back everything, then you are having a stress induced. This stress is called as thermal stress, and the formula for the thermal stress is alpha into delta T into E. Okay. This is case number 2. That is fully restricted and you don't allow any expansion at all. Okay. Now let's go to case number 3. In case number 3, what we are doing, we are partially restricting it. See here. So partially restricting it. See, you have your L naught here. This side I am blocking it. Sorry. Now what I am doing now, I am just okay. Now if you allow it to expand completely, free expansion is from here to here. But I am not allowing it to expand freely. There is some amount of space here. There is some amount of space here. This much I am not. This much the material can expand. Beyond this, it cannot expand. So how much I am preventing the expansion? I am only preventing this much of expansion. So only because of this, some amount of stress is induced. Okay. So now here you see, you have the formula. PL by AE is equal to, the free expansion is how much? Free expansion is alpha delta T into L naught, correct? But how much you allowed to expand? You allowed to expand. This is not, I mean, here in the picture he has used it. This is basically delta, okay? This is basically delta. So this much you are allowing it to expand. So minus it, okay? When you minus it, only you are stopping this much. Only you are stopping this much of expansion, correct? So I can write sigma into L naught by E is equal to this much. So go to the next slide. What can I write now? I can write sigma is equal to, you can simply say, you take E on this side, E divided by what you can say L naught into alpha delta T into L naught minus delta you can write. Otherwise, you can only use this formula. When we solve the problems, you will know it. Okay. This is for partially restricted case.